This is part 2 of the video lecture for indeterminate forms and L'Hopital's rule. Last time we talked about indeterminate expressions, which are expressions which can take on more than one value depending on the formulas or the functions which got you there. In particular, we mentioned 7 different types of indeterminate expressions. 0 divided by 0 is kind of the basic one, but you also have infinity divided by infinity, 0 times infinity, infinity minus infinity, 0 divided by 0, infinity raised to the 0 power, and 1 raised to the infinity power. And each one of these can actually be rewritten in terms of 0 divided by 0. Again, the normal rules of arithmetic don't apply to infinity, so as tempting as it might be, you can't reduce infinity divided by infinity to 1. You can't write 0 times infinity is equal to 0. It depends on the expression that brought you there. So to figure out which of the many values is valid for each of these expressions, we're going to use a rule that was developed by the Marquis de L'Hopital. Now we just call it L'Hopital's rule. And it goes something like this. L'Hopital's rule says, well, one version of it says that the limit as x goes to c of a function is 0, and the limit of x goes to z of another function is equal to 0. Now let's say you're trying to calculate the limit of the quotient of these two functions. Now, if you were to just plug in c to these functions, you'd get 0 divided by 0. You get an indeterminate form. But whatever the value of this expression truly is, it also is equal to the limit of the derivatives of these functions evaluated at c. Now, something to be very careful about is L'Hopital's rule says to calculate this limit, in other words, take the derivative of the numerator, take the derivative of the denominator. No, we're not using a quotient rule or anything here. We're not taking the derivative of this fraction. L'Hopital's rule says the limit of this kind of expression is the limit of the derivative of the top divided by the derivative of the bottom. To kind of help you remember something like this, I always think it's better to figure out where this rule came from. So specifically, we're going to look at the case where f and g are two functions that are pretty nice functions. They're both differentiable and their derivatives are continuous. So to see why these two expressions are equal, what we're going to do is, well, a bunch of algebra. We're going to start off with a limit of f of x divided by g of x. What I'm going to do is I'm going to subtract 0 from the top and the bottom. Remember, the limit as x goes to c, f of c is equal to 0, and so is g of c. So this fraction has the same value. And then, again, without changing the value, I'm going to multiply this fraction by 1. And multiplying by 1, I mean 1 in this extremely clever form. And then, multiplying through the numerator and the denominator, notice I'll get this wonderful compound fraction, right? But these expressions might start to look familiar. They kind of look like slopes. And in fact, the limit of this fraction, now I'll expand the limit out. I'll do the limit of the numerator divided by the limit of the denominator. And notice the top, that's one of the definitions of the derivative of f. And the bottom, the denominator, this is one of the definitions of the derivative of g. So on the top, we have f prime of c, and on the bottom we have g prime of c, which I'm going to rewrite, again, as another limit problem. This is the limit as x goes to c of the derivative of the top divided by the derivative of the bottom. So again, this is why this expression up here is equal to this expression down here. But remember, this only works if you have an indeterminate form. Okay, so let's take a look at a problem we looked at in the last lecture video. Let's try to do the limit of this expression right here. Now, again, this is an indeterminate form. If you were to just plug in 1 for x here, you'd have 0 divided by 0, and that's indeterminate. One way to solve this is by using clever algebra. Since the numerator is a difference of squares, you could factor it, then you could do some cancellation, and then you're left with the limit as x goes to 1 of x plus 1, and that's just 2. Now, L'Hopital gives us a way to calculate this without using clever factoring. So we can use L'Hopital's rule because we have an indeterminate form. Remember, that says to find the limit of this quotient, it's the same thing as the limit. We're going to do the derivative of the top and the derivative of the bottom. Well, the derivative of x squared minus 1 is 2x. The derivative of x minus 1, that's 1. And now, if you plug in x equals 1, you get 2 times 1 divided by 1, you just get 2. Again, you're getting the same answer here, which is good. Math is consistent. Again, L'Hopital's rule can be used in situations where you're not sure how to factor it or when you're not sure how to simplify an expression. So let's try another problem. After all, you learn math by doing math. Okay, let's say I want to evaluate this. I'm given the limit as x goes to 0 of x times ln of x. Now, if we were to just plug in 0 for x and ln x, we would get an indeterminate form. We would get 0 times ln of 0, but ln of 0, that goes to negative infinity. So, I'd like to use L'Hopital's rule. But remember, L'Hopital's rule only applies if we're looking at fractions. So what we're going to do is first somehow rewrite this as a fraction. And there's a couple of ways to do this. To make the derivatives as easy as possible, here's what I'll do. Get the limit of x times ln of x. I can rewrite x as 1 over x inverse. Right? So this fraction right here simplifies to what I'm originally given. And so now this is in the form where I can use L'Hopital's rule. Since this is indeterminate, this is infinity divided by infinity in this case, L'Hopital's rule says the limit is the same as when I do the derivative of the numerator and the denominator. The derivative of ln x, that's 1 over x. The derivative of x to the negative 1, that's negative x to the negative 2. And now I recalculate the limit. Well, first I'm going to do some algebra and simplify this. 1 over x, I'll put that x in the denominator. And negative x to the negative 2, that negative exponent, I'll move that up to the numerator. Now I've got some really easy cancellation. X squared divided by x, that gives me x. And this limit, as x goes to 0, is 0. So this expression right here, it looks like 0 times negative infinity, but in reality it actually simplifies to just plain old 0. Let's do another example. Let's see. Here's a good one. Limit as x goes to infinity this time of e to the x divided by x squared. Again, you have an indeterminate form. If you were to just plug in infinity, you would get e to the infinity divided by infinity squared. An indeterminate fraction, so we'll use L'Hopital's rule. So it says we'll take the derivative of the top, the derivative of the bottom. The derivative of e to the x is e to the x. The derivative of x squared is 2x. And you plug in infinity, and whoops, you get infinity divided by infinity. Still indeterminate. Well, as the saying goes, if at first you don't succeed, try again. And by try, I mean use L'Hopital's rule again. So we'll take the derivative of the top, the derivative of the bottom. You get e to the x over 2. And now when you plug in infinity, it's no longer determinate. You get an infinite number divided by 2. In this case, it's actually not indeterminate. This is truly an infinite number. So in this case, you say the limit diverges to infinity. This number just keeps getting larger and larger as x goes to infinity. Let's do another. Still have some time, right? Sure. What else are we going to do? The limit as x goes to 0 of x to the x. What a crazy looking function. As x goes to the 0, you get 0 to the 0 power. So again, we've got an indeterminate form. We'd like to use L'Hopital's rule, but before we can do that, we have to rewrite it as a fraction. So here's how we'll do it. To get rid of this variable in the exponent, first I'll say, let y equal this whole limit expression, and then I'm going to take the ln of both sides. ln of y, well, I'm going to do the ln of this function, and the ln of x to the x, this x in the exponent, and come out in front by the rules of logarithms. I have x times ln x. This sounds kind of familiar. But I need to rewrite this as a fraction still, and I can do that by saying, okay, x is the same thing as 1 over x to the negative 1. So I'll rewrite it as a fraction, and then I'll do the limit as x goes to 0 of this. Now I still have an indeterminate form, infinity over infinity. So using L'Hopital's rule, I do the derivative of the top and the derivative of the bottom. Get 1 over x divided by negative x to the negative 2. We actually did this a couple problems ago. So after some simplification, again you get 0. But be careful, we're not done yet. The limit isn't 0. Remember we calculated ln of y, the logarithm of y, to be 0. So since the logarithm of y is 0, that means y must be e to the 0. In other words, y is equal to 1. But remember, y was originally this limit problem, so this limit of x to the x is in fact 1. Actually, if you graph this function, you could even see that x to the x does in fact approach 1 as x goes to 0 from the right. Here's a fun looking one. The limit as x goes to 0 of the quantity 1 plus sine of 5x raised to the power 1 divided by 3x. So again, this is an indeterminate form. If you plug 0 right in here, you'd get 1 plus 0, so you get 1 in the base, and 1 divided by 3 times 0, get infinity to your exponent. And 1 to the infinity, again, that's not necessarily equal to 1. This is truly an indeterminate form. We can rewrite this as a fraction, and then we'll use L'Hopital's rule once more. And, like the previous problem, we have y equal to this limit, as x goes to 0, of this expression. To deal with this variable quantity in the exponent, we're going to take the ln of both sides. So ln of y, the limit of ln, this expression, and the exponent, 1 over 3x, comes down in front of the ln by the rules of logarithms. So here's our new transformed limit. Now it really looks like a fraction. We have the limit as x goes to 0 of ln of the quantity 1 plus sine 5x divided by 3x. And if you plug in 0, you notice that, hey, I do have this weird indeterminate form. I'm getting ln of, well, 1 is 0, and 3x, well, that's 0. I've got 0 over 0. So what do I need to do? L'Hopital's rule says do the derivative of the top, the derivative of the bottom. Okay, I can do that. The derivative of the top, that's going to be one big chain rule. We've got function inside a function inside a function. So the chain rule says, here's my derivative of that. Derivative of 3x, that's 3. So now what happens if I plug in 0? Well, fortunately, I don't have an indeterminate form. I actually get 5 over 3. So I now know that the ln of this limit, ln of y, is equal to 5/3. That tells me y is equal to e to the 5/3. So the limit of this complicated expression is e to the power 5 over 3. I think we've got time for one more. Let's do the limit as x goes to pi over 2, tangent of x minus secant of x. Now, both of these, as you get closer to pi over 2, tend to infinity. So this expression is the indeterminate form, infinity minus infinity. We'd like to use L'Hopital's rule, so as always, we'll rewrite as a fraction, since it's not already there. Use L'Hopital's rule. Well, tangent is sine over cosine, and secant is 1 over cosine, so I can actually combine these into a fraction pretty easily. And now, L'Hopital's rule says, oh, if I plug in pi over 2, I'm going to get 1 minus 1, that's 0, over cosine of pi over 2, that's 0. I have the indeterminate form 0 over 0. So to evaluate this, I'll do the derivative of the top and the derivative of the bottom. I'm left with cosine on top and negative sine on the bottom. And now if I plug in pi over 2, I get the nice easy fraction 0 divided by negative 1. So in this case, the answer is in fact 0. The limit of this expression, infinity over minus infinity, for these specific functions is equal to 0. And there you have it, L'Hopital's rule in action.